Hello, everybody. Welcome to today's Crunch seminar. Today we have two speakers, two talks. Our first speaker is Professor Chen. He will be giving a talk on can video generative models learn and generalize physics-based control signals. Chen is an assistant professor of computer science at Brown University, studying computer vision, machine learning, and artificial intelligence. His research focuses on multimodal concept learning and reasoning, as well as controllable, principled, and scalable image and video generation, and their applications in robotics, planning, and control. Chen received his PhD from the University of Southern California in 2016 and bachelor's degree from Tsinghua University in 2011. Chen received a Salmon Faculty Research Award from Brown and Global Research Outreach Award from Samsung. His work appeared in CVPR's Best Paper finalists. With that short introduction, the floor is yours and you can start your presentation.
Thank you so much for the kind introduction. And I know my research background is probably quite different from most of the audience here. So if you have any questions, feel free to interrupt me at any time of my presentation. And today, I'm going to present something less related to multimodal learning, less related to like large language models or agents. Sorry, George, we do work on those, but I'm going to show something like some, in my humble opinion, recent breakthroughs on like controllable video generation. And at the end, I will show one concrete application on like robotic decision making. Okay, and the title of the talk is Video Generative Models, Can They Learn and Generalize Physics-Based Control Signals? I know physics is a very like a broad term, and we have a very humble and narrow definition, and this is what we mean. Like you can show, I'm not sure if people can see the videos. Let me try again. Yeah, so it's basically like point-based forces. That is the thing that we are considering in the context of my presentation. You can either poke a ball. I'm not sure if people see my mouse cursor.
Yes, yes.
Okay, cool. And you can either like poke a ball and or drag a flower or other some deformable objects or rigid objects. And this is during training. And during video generation, we hope to generalize to more like realistic, realistic scenarios. Okay, and this project is led by my PhD student Nate Gilman. He's has a very unique background. Like he's a mathematics PhD, interested in machine learning, and you can see that he's doing a series of amazing work with our amazing collaborators, both undergrad and PhD students at Brown, and a few senior researchers at Google DeepMind. Okay, so the bulk of the talk, I'm going to talk about our NeurIPS 2025 paper, and we also have an ongoing submission as a follow-up. Okay, cool. So if you follow the machine learning or deep learning like trends, okay, so there's a buzzword that come up very frequently nowadays, that is world models, okay? And the interesting thing is that different people have different definitions of world models. And if anyone in the audience have their your own definitions, feel free to speak up. But my personal understanding of world models is basically action conditioned state transformation of the environment, okay? And the world is basically what the embodied agent is situated in, okay? But nonetheless, like because world model is becoming such a buzzword, so many different people have their own definitions, okay? And including one of them is video generation, which we will discuss. Can we turn like video generative models into a real action conditioned like state predictors, of course, in the pixel space, okay? And people have accomplished some of the successful applications of building video-based state transformation models. And one particular scenario is self-driving. Let me show the video. So all of these like street views are generated by a neural network. Okay, they look pretty realistic, and you can imagine that the sequence of frames are conditioned on the inputs from the user, where to control the vehicle, which direction the vehicle should go. Okay, and another like so so I believe this is like not real time, but people have developed a lot of engineering improvements on the video generative models to make them like real time. And this is an example. Okay. So you can navigate in this like a video game-ish environment and explore around. And this is probably from 1 year ago. And if you take a look at the recent developments, such as I think Genie 3 is probably one of the more like high-profile ones. They achieve quite impressive like performance with like temporal consistency, 3D structure consistency. Okay, so that is really good. Let me see if I can hide. Okay, so that I'm not blocking. Okay, cool. So if you notice these like actions, they're actually just navigation in the environment or redirecting the camera angle. Okay, so we have clearly a missing piece that is like interact with the environments, with the objects. Okay, and here is what we consider as one form of interaction is that you poke some objects. Okay, and the yellow arrow dictates the direction of the force and also the strength of the force. Okay, and this is my daughter, and I'm just trying to brag about how good our method works on random user uploaded photos. You will notice some of the artifacts, which I will explain like how we mitigate those through the huge rapid progress of video generative models. Okay. And we also consider a global force is the wind force field. And you can see that, again, we direct the direction and possibly the strength of the force. And in this case, it's like trying to use the wind to blow the hair. And you can notice if you are like a kind of a visual content creation person or like a graphics person, you may notice that, okay. You may notice that one interesting thing is that the background wave, sometimes they move accordingly to the global force as well. Okay, so so far so good. So how do we accomplish this? People have long been interested in like making video generations more like realistic in terms of like intuitive physics, right? So they need to look good to average person. And even 2 years ago, when Sora was very popular, the video generative model demo from OpenAI, people quickly noticed some of the like failure modes of those models. That is, they hallucinate a lot, like from like four-legged ants to like basically the arm morphs in weird shapes. And also another thing is that they notice that they look the physics, the dynamics of the scene look wrong even to like average human, which make it like hard to directly apply them to even for content creation, let alone like robotic decision making. Okay, and people have thus explored, I guess, a few different, I may say, complementary approaches to fix this. Okay, and the first approach is to use like a rule-based physics simulator. By rule-based, I mean like those physics simulators are programmed by experts. Okay, and then once you have the physics simulator, you can try to re-render them into photorealistic videos. I purposely like show this very humble looking like a human skeleton moving around for two reasons. One is that it highlights like how like physics simulators takes in like sparse information like human body key points, and it may not be able to handle more complicated scenes. Okay, and the second is that this is actually based on some of the results we obtained in an ICML paper published 2 years ago. Okay, but you can imagine that is the idea. Okay, and the human body movement is implemented by some experts in a physics simulator. Okay, and here's another example. Basically, you can have like not only human skeleton representations, but for more general deformable objects, you can try to build a representation in terms of meshes, in terms of 3D Gaussians, and then trying to run the simulator, and then try in response to some of the user input. And user input is like the force applied on the objects. And then you run the simulator to generate the sequence of the representations, and then use video generative model, use a neural network to re-render it into a nice looking video. Here I took the figure from the original paper, but later on I will show some real results, and that will be actually a quiz for you. Okay, so stay tuned. Okay, so here I'm basically trying to dig more into the first approach, but some of you may already notice there might be some inherent limitations about this approach. Okay, and one possible idea is that we can first trying to build a neural network to generate a sequence of human body movements. Like let's focus on this human motion generation task because we have a preliminary work and also because it's easier to explain. Okay, and then once we have the sequence generated by a neural network, we ask the physics simulator to correct the model's responses, such as in this case, you can see that in this case you can see that the hand penetrate the arm. Okay, so this is based on the generation from the neural network, and later on we ask a physics simulator to correct that. Why do I combine the two in this fashion? The motivation is that you can leverage the huge expressive text to motion generative capabilities of neural networks while still maintaining like the physics obeying properties after the correction. Okay, and we can all think about how to implement this correction function, which I will show in the next slide. Okay, but this is the result as we show in the ICML paper. After the physics correction, you can see that the penetration is fixed. Okay. And to make this work, we need a few things. We first need a physics simulator, and the physics simulator needs to generate a sequence of human body motions. And it also needs to take in the input, the sequence of human motions generated based on a neural network conditioned on some user input. And the user input could be describing the human's actions and the sequence of actions, right? Once you have the physics simulator, then you're trying to run the reinforcement learning algorithms to train a policy to imitate the user's input, which is sometimes incorrect, inside this physics simulator, which is by definition and by implementation always correct according to whatever implemented in the physics simulator. And you can imagine how to train this policy is that you can generate a whole bunch of diverse human body movements and train a reinforcement policy using a reward such as the L2 distance of all the body key joints based on the policy and based on the difference between the policy's output and also the target motion sequence. Okay, that will be your reward. And once you train that policy, you freeze it because training this reinforcement learning policy is so expensive, you just assume this will generalize. And whenever you have a new motion sequence generated by some neural network, you run the same policy and trying to imitate the sequence inside this physics simulator. And this is what we call physics correction step. Any questions so far? Okay.
Yes.
Yes.
I have a question, Professor Jensen. Can you please explain what the physics simulator is in this context?
It's basically trying to respect to the gravity and trying to make sure the motions of the human body skeleton need to be properly configured in order to accomplish certain actions, such as instead of trying to roll around on the ground, trying to actually stand and walk, something like that. Does that
It's
make
like
sense?
a pre-existing model outside of the deep learning framework that you could use.
Yeah, it's more like an environment. I'm not sure, for example, in deep learning classes, we talk about reinforcement learning and
Yeah.
we try to make a human walk in that simulated environment, right? And that is basically the same thing. You need to take the enough correct actions in order to make sure the human actually walk in that physics environment, simulated environment. Make
Thank
sense?
you.
Hello, Professor. I had a question too. So, like, could you explain what do we mean by correction here? Like, why do we have like two phases where we have a neural network prediction first and then a reinforcement algorithm after that?
Okay, so whatever is on the left is trained purely on a data-driven basis, meaning that you have paired data. The paired data is like human motion sequences, like in 3D and /4D space, paired with some text descriptions describing the human's activities. And you can imagine you train a generative model such as diffusion model, and to fit the training data. And the neural network itself, it doesn't have the notion of like the hand penetration or whatever. It's just trying to solve whatever is dictated by the diffusion training objective, right? Trying to reconstruct the training data. So that is the first phase. The first phase is good at trying to translate human prompts into like the human motion sequences, but it's bad as potentially bad as at respecting the physics of like the human motion. Okay, and the second phase, the reinforcement learning stage, it has no notion of text conditions. It's basically the input only is a sequence of a neural network synthesized motion sequences, and is trained to translate that to whatever can be executed in this simulated environment, with a hope to minimize the distance between the machine, the network synthesized motion sequence and the environment executed motion sequence. So basically, the first stage is trying to translate text into motion sequence, and the second stage is trying to translate possibly incorrect sequence of motion into whatever can be executed by this physics simulator, which by definition should be correct because it obeys to the laws of physics, however implemented by the simulator. Does that make sense?
Yeah, that makes sense. Thank you. So is it like a frame by frame prediction? So for every frame you have a neural network prediction and then there's a correction step and then the next, that's how it rolls out. Is that how it works?
So we are doing a non-causal diffusion model. So the prediction is by chunk. So for example, we predict 40 time steps all at once. So the input to the physics simulator is also like all those 40 time steps.
Okay, got it. Okay, thank you.
Okay, feel free to
Hi.
ask me more questions.
Yeah. Hi, Chen. I have a question here. It's highly interesting. So I guess the representation of the physics law or the physics simulator is a kind of low dimension like representation, right? So my question is, it's like a hidden state which we cannot understand, or it's like what you show like in the for human body. Yeah. This kind
It's
of
like
points
this.
that we can understand.
We can understand, but you can imagine this is a very coarse model of the human body, right? So, but this is whatever was implemented in the physics simulator we use.
So it will be specific to different kind of object, like for cars, for human body, for like the flowers.
Exactly. And you highlight the limitation of this approach. And we actually had a hard time trying to generalize this human body model to a different one with a few more key points because it's not implemented in the simulator. So this,
yes, thank you. So is there an automatic way to like extract this kind of lower dimension representation from any objective?
So that's a great question. So there are people in computer vision actually were quite interested in this 5-10 years ago. But even you have the key points, you still need, if you want to use this like a simulator-based correction, you still need to implement the laws in that simulator. And that part is probably the most time-consuming part, if that makes sense.
Yeah, got it. Yeah, thank you.
Yeah, cool.
Hi, Professor. I have one more question. So if you go to the video of your daughter, there is the branch swinging around, if you showed in your slide.
So which one? Could you help me?
The video of there is a small girl and there is a branch which is swinging, like you are showing
Oh,
the
this one.
motion. The one before, I think the one more, like
This one?
no, that again more previous. There was a branch swinging on, I think.
Oh, maybe your question first, and then I will
Yeah,
try
so
to.
I think I show a shadow, like because when you trigger the motion, there was shadow coming on the face of the girl. So I was just wondering whether did you do some
Oh,
specific about the shadow part, because I don't know if
oh,
that's in according to the physics, right? That's very
yeah.
realistic. I was just wondering.
Okay, this
Yeah,
one,
here,
right?
yeah, this one,
Yeah,
yeah. So when
yeah,
you swing it, right? So it has a shadow coming in.
yeah. This one, right?
Um, yes,
Yes, yes. That's a great observation. This is how the video prior may help us avoid a lot of the complicated modeling issues. So basically, I think the diffusion model was trained to generate a photorealistic videos, and the shadow is basically directly generated by the whatever prior baked in the neural networks. So we didn't need to specify it.
Okay, understood. Thanks.
Okay, yeah. So yeah, I also like the shadow part, but you can imagine this wouldn't work 100% of the time, right? Because it's a neural network, and there are still many failure modes of this like neural network-based video generative models. Okay, let me try to resume. So we have discussed the potential limitations of this approach, which is great. But when it works, it can be quite helpful, right? Like we have a thorough discussion that implementing this is highly non-trivial, right? You want to implement the correction function, which requires a physics simulator, and also you need to have 3D asset of the humanoid, and it's just we probably use the simple model. And it may not generalize to other like 3D assets of the humanoid, not to mention other objects. Okay, and of course this is a lot of engineering efforts, and our implementation is actually based on a long line of open source code released by other like pioneers in the field, such as from CMU, those researchers. Okay, so it's non-trivial. It may not generalize, and I will skip this part, but our original motivation was trying to do something like this. And the motivation is that we were part of the researchers that varied the pollution caused by like generative AI, meaning that users upload their favorite machine-generated photos, videos, text to the internet, and those may be later on downloaded to create the training data to train a new generation of generative AI models, and we call this like paradigm of feeding the model's output as the input during training as the self-consuming. And then there was a paper by researchers at Stanford and the Rice University. They observed that the generative models training may collapse if you keep on feeding the training their own like generated data as the training data. Okay, and here's just an illustration, again, using this simple humanoid example. And this is basically showing I believe, over 50 iterations. Like the baseline approach is still do reasonably well, but this is basically trying to like do some crazy movements. And I think the text prompt for this example is maybe standing, something like that. Okay. And I will skip our theorem, but basically the takeaway is that if the correction function is good enough, we have certain assumptions on what the correction functions can do in a probabilistic fashion to match the true distribution, and then the resulting generative model will be excellent. Okay, and here are just some of the result. The text prompt is that the person standing with feet wide stretches both hands up over his head and then swings down by blah, 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 blah. And you can see the examples, okay? So the baseline is basically without any, like, if I remember correctly, without any self-consuming training, so the initial model, Okay, so it's doing okay. And the second, the green humanoid is after like 50 iterations of self-consuming training, it basically collapses into generating something weird. And the last column is like self-consuming training, where before we trying to reuse machine-generated data for next iterations model training, we correct them using our like physics corrector. And you can see that it avoids models from collapsion, from being corrupted, and that basically provide one empirical support to our like hypothesis. Okay, cool. And of course, this approach requires a physics simulator and also the modeling of all the objects of interest in that simulator. And generalization beyond human motion can be like highly non-trivial. Okay, so any questions so far before I move on to the second approach? Okay, so what we are trying to explore is that we were kind of excited about what we were able to do with this toy example, but we really want to scale up our approach to more general photorealistic videos. So we don't want to rely on 3D assets or like physics simulators at inference time, okay? And why? Because our assumption, which many of you may not agree, and I personally have like some reservations, but still, like if you look at the progress made in the neural network-based video generative space, I think you will be impressed, or I have been impressed. So this is around 1.5 years ago, state-of-the-art model by them called Coq Video X. This domino blocks, I think it doesn't like really do anything well, okay? And this is the same scene like generated by a newer model called 2.2. It's released exactly 6 months ago, okay? And the condition for both neural network-based video generative models are the first frame. So they accept the same information. The first frame is an image, and then the text prompt, probably in this case, will be like the falling like domino blocks, something like that. Okay, so the progress is very fast, and we hope that we can directly benefit from this progress, just like the branch and shadow example one student or one of the audience just mentioned. Okay.
Hi, Professor. I have a small question here. For the second case that you're showing in the bottom, this is just purely data-driven from their side, right? So they didn't try to include any type of physics knowledge or anything here.
No.
Oh, and in the case, their trick is just adding more data. What is the trick to make the model respect the physics a bit more if they don't encode any physics?
So this is a great question. So again, like I need to double check, but most of these models were not trained. They did not release their training data. So we don't know what's inside their training data, but I assume that part has been constantly progressing as well. And the other improvement will be the model architectures. But it's, for me, at least to my reading, it's hard to tease apart which particular like neural network design leads to like better modeling of this temporal dynamics of the domino blocks.
Oh, okay, that makes sense. Thank you so much.
Yeah. So, but there is no explicit laws trying to penalize like trying to bake in the physics priors when it comes to this thing. Okay, that's a great question. So our dream is that we want to inject causal control signals for interactive video generation. So during training time, we may rely on like some of the physics simulators, which I will show how in a bit. And during inference time, we want to completely rely on the neural network because they are becoming better and better, and also because if it works, it will be a quite scalable approach. Okay. And before we dig into our particular proposed method, I want to share two related work. Okay, so this related work, they rely on physics simulators during generation time or during so-called inference time. And the figure is a little bit complicated, but the highlight is that basically given an input image, what they do is that they want to do inverse rendering, basically turn the image into like the normal and albedo and the segmentation of different objects, okay? And given the object information, they run a physics simulator during inference time, both training and inference time, to like produce the sequence of like plausible temporal trajectories for each like individual objects in the scene. Do we have a question? Yeah. So, and then once they have this like object-centric representation, they conditioned on the initial frame and conditioned on the quote dynamic simulation to do the re-rendering, okay, to generate a photorealistic sequence of objects. And this is one approach. And this is another approach. They are doing basically essentially the similar idea, but you can imagine the dynamic simulation requires like a human programmed physics simulator, which may not be scalable to different like type of objects, right? And what they do in this second paper is that they trying to train a neural network-based physics simulator by distilling information from like a human programmed simulator. And their hope is that this will lead to some generalization to new objects behavior, okay? But the overall framework is very similar. You do inverse rendering, turn an image into a more structured 2D or 3D representation. You run your physics simulator during generation time, either in terms of the object-centric 2D representation or in terms of, in this case, a point cloud. And then finally, you do like video generation or the condition video generation, which is commonly referred to as re-rendering, okay? Okay, any questions about the baselines? If not, then you probably will agree that this approach also has a certain amount of limitations. And here's a quiz, okay? So I think I mentioned a baseline approach called PhysDreamer. It's very good at simulating the Planck's movements, okay? And my question for you is that which one is generated purely neurally without a simulator during inference time, and which one does require a physics simulator during inference time? Anyone want to quickly shout out? Okay, I assume the silence pretty much indicates that it's hard to tell, okay? And but otherwise, let me know. So the first row is from the baseline approach, and the second row is actually from our approach, which we call force prompting. Okay, there's like a caveat. I think if you look really, really carefully, you can still tell that the PhysDreamer looks nicer compared to our approach, like under very super high image resolutions, because our model is trained on like 480 by 480 like resolution. So there are some artifacts. But at this, whatever is presented, in my humble opinion, they look close enough. And our approach is purely neural network based. So how do we accomplish that? Okay, so let me try to move this bar again, not to block. Okay, so our assumption is that we assume the video generative models, they are progressing fast, and they also encode very strong visual and motion priors. For example, if we give a initial image, this windmill, and then we give a text prompt, windmill turns, it will just like generate quite like photorealistic videos. The only thing is that it's hard to control, like if like the specific like motions or the forces we apply on top of the initial images, okay? And we're basically trying to inject this physics-based control, in our case, force-based control, using synthetic data, okay? And this is our synthetic data where we have ground truth information from the simulator, which we use Blender to like unroll how the objects will move conditioned on the input force and the direction and its magnitude. And then it will allow us to do this kind of generalized force control, okay? So you can see that now we can control. If we poke the windmill to the right, it will rotate to the right, and otherwise it will rotate to the left. Okay, so any questions about this slide?
So that doesn't mean that it's correct, right?
Sorry?
It doesn't mean that the rate, that a rotation rate is correct.
That's exactly right. So basically, this is intuitively, it looks nice. But if we try to have some of the quantitative evaluations later on, but also it's hard to have a very controlled quantitative evaluation given arbitrary
For this example, the wind in these farms comes in bursts. So it's an intermittent. So how could you include intermittency in the force?
That's a great question. So our control signal is basically the direction and the magnitude of the forces over time. So ideally, if you have the corresponding simulated data, you can use that for training. And whether it will generalize or not, we haven't tried, but we don't know. So a data-driven approach is possible, but I'm not sure how well that will work.
I don't think it is, because in these systems there's some memory. So what you do instantaneously does not necessarily, that's why you have the rate derivatives, right? And now Newton's law and so on. So there is a little bit of memory, especially in a float system. So let's say that this is artistic but not scientific.
That I fully agree with. Yeah. And we can probably, if we have time, we can discuss at the end of the presentation, like what will be a principled approach to make like those video generative models like obey the laws of physics, not just relying a data-driven approach, pure data-driven approach. Yeah. But basically, what I'm trying to show is that it does something, it looks nice, and we have some preliminary results showing that it's to some extent respect the input signals in a quantitative way. Okay, yeah. So let me see, and here are some of the more like examples. Trying to poke a train, and you can see that again, like most of the heavy lifting depends on the strong motion prior already baked in the video generative models, which, as George mentioned, very likely this is some of the correlation remembered during training time on some of the training videos. Okay, but nonetheless, does feel quite impressive, and it does generalize to many scenarios, such as my daughter's photos. Okay, cool. And here is basically another example. I wouldn't bore you with this. So our training data, I think the most surprising information observation we had in this project is that to make like a pre-trained model understand physics-based control signals, you don't need like real data, you don't need diverse data, and you don't need very scaled up data. Okay, so we only have around 10,000 to 20,000 short videos, and all of them are generated by Blender. And for wind, we basically, I'm not sure, consider like flying flags over some random background. And for like point force, we basically have the balls rolling around. Okay. So I guess now the anticipation is high that this will generalize pretty well. Okay. And here are some of the demos. It generalized to hair, generalized to like this hanging like horse. We show this like windmill example. And our model, to make sure that this model is trained properly, we rely on some technique called control net. So control net, the high level idea is that we all know that if you fine tune a neural network in a naive way, it may like catastrophically forget about whatever was whatever tasks and data it was trained on. And indeed, if we directly fine-tune a pre-trained video generative model on our synthetic data, it quickly turns the model into like a flying flag generator and forgetting about everything else. And basically, the control net paradigm is trying to keep the original weights frozen. So the pre-trained information is always there. And they're trying to create copies of certain layers of the weights and then trying to modulate the neural network using the new training data by updating some of the, by fine-tuning some of the copied weights in the sub-neural network. Okay, so that is basically the high-level explanation of what a control net is. Okay, so you have our training paradigm is, again, image and text conditioned, but now we add the force condition signal, and then our training objective is basically to generate this flying flag video or balls rolling around video. Okay, and how do we represent the force control signal in control net, as George previously asked? That is, we basically represent the control signal as another video, but this video is a Gaussian blob moving around, and you can imagine the location of the Gaussian blob represent where the force is being applied to, and the speed of the Gaussian blob represents the magnitude of the force. And there are obviously two caveats. The first caveat is that this looks super simple. Have we tried more complicated representations of the force? We haven't, because this is the first thing we tried and it just worked really well, that we didn't want to overcomplicate our design. And second question is that this design indeed introduced a challenge for quantitative evaluation, because we rely on the force annotations from a physics simulator, which we use Blender. And the Blender force is not calibrated with a real world. So we don't really know like the certain speed of the Gaussian blob moving, how that corresponds to the real world forces. So that we basically, all the quantitative evaluations basically later on we show that there's a linear relationship between the distance an object travels with respect to the force, the magnitude of the force we applied on those objects. Okay, and of course those are the things that can be improved. Okay, and we're trying to evaluate our approach using three metrics: force adherence, which is the most important one, and also realistic physics and the visual quality. Okay, and here I cannot find my cursor, but okay. So here we're comparing to one prior state-of-the-art approach, motion prompting, and we also compare with some of the obvious baselines, such as we just use the pre-trained model and either ask it to generate the forces by specifying the point force or wind force using natural language as opposed to our additional input signal. And the second baseline, the second line of the comparison is basically we are trying to fine-tune the baseline model and see if it does better. And of course, this is a human evaluation because everything in video generative space is hard to design or trust the quantitative evaluation metrics. So we report those, but we always trust the human studies more. And you can see that compared to all baselines, we do much better in terms of the force adherence, and the realistic physics and the visual quality is basically on par to the baseline model without fine-tuning. And this basically reflects our assumption that our method is not trying to improve the temporal dynamics and the appearance modeling of a pre-trained video generative model. It's basically utilizing it and with the hope that we are not breaking the prior information already baked in those video generative models. And our fundamental hypothesis is that as more and more powerful, of course, data-driven video generative models are being developed, then our approach will naturally benefit from the better models, which we indeed show later on. Okay, so here are some of the. Yes.
Okay, so I have a quick question here. when you when you evaluate like this realistic physics, like how is the evaluation done? Like that's
Yeah, this is a great question. Again, like I personally don't like this terminology, but it was, I believe we reuse it from a previous baseline paper. It's basically, you can imagine this is like intuitive physics, right? Where the video look nice, or to quote George's comment, artistically looking nice to a human like user based on the visual quality and also the motion quality. So, but there's it's not reflecting how actually these are like re-implementing a physics simulator in a neural network. Does that make sense?
yes, but when you assign a number, so it's like visually physics looks physically correct. So you mean you have like humans evaluator that looks at the pictures and gives him a score or something like that?
Yes. So we have
Oh.
a description of our definition of like what we mean by realistic physics, and then we have side-by-side comparison of our generative video and the baseline generative video, and we ask the human rater to choose which one they think is more photorealistic or like motion realistic, and or they are exactly the same. Does that make sense?
Yes, that makes sense. Thank you.
Yeah, cool.
Professor, I had one more question. So, like,
Yeah.
could you explain like how are we doing the conditioning? Like, for example, when you give like a force input, how is that being translated to the model? Like, do you give some local embedding of where the force is being applied and the magnitude and the direction of the force? Like, could you explain that?
Okay. So remember, we're using control net, right? And control net is basically trying to create a copy of the certain layers of the original network. And the original network basically takes in an image or a video as input, and then outputs another video, right? So to use control net, we also want to parameterize our force information into an image or into a video. That part is clear?
Yeah.
And so how do we represent force as a video? This is what this slide is trying to show. It's basically trying to have a Gaussian blob moving around across frames. And the speed of the Gaussian blob basically represent like the strength of the force.
Okay.
So the Gaussian blob is the output of the control net?
Input.
The input to the control net. Okay.
Yes.
So do you have like a label that shows the swinging faster by any chance to fine tune the network?
So we basically if you look at sorry, I cannot find my mouse cursor. Oh, yeah. But if you look at the frame 0, there are two light blue arrows. It's trying to show where the force is being applied and the magnitude. And that basically, later on, you can see that the first row, the magnitude is lower, so the Gaussian blobs moves slower. And the second row moves much faster.
Okay.
Does that make sense?
But no, my question was, how does the network know like the going faster implies the swing should go faster? That was my
Yes, that is basically in the data-driven approach. The only training objective is not to obey the physics, the force-based control signal. The only objective is to generate a nice-looking video that looks similar enough to the ground truth video, right?
Okay.
Yeah.
Okay. Thank you.
Yeah. Cool. So I will try to wrap up my presentation really quick, and then so that we can have some time for discussion. Okay. So again, I don't want to oversell our approach by saying there are emergent properties, but indeed, there are some interesting observations here. Like, for example, we compare like applying the same force on like 3 books over compared to 1 book, and you will imagine the single book will move faster and farther distance compared to the 3 book. And similar things happening for this laundry basket full of dirty clothes or empty. And 2 blocks, 1 block, and then this heavier looking like horse pendant, and this lighter looking like wood pendant. Okay, so basically everything, again, we don't provide mass information to the model. And our expectation is that because the video generative models are trained to generate nice looking videos that look like whatever the training data will be, so they need to have a implicit understanding of the properties of the objects in the initial image, like the mass, how heavy, where the object is tied to. Okay, so that is one thing, and it sort of understand affordance, and this is I cannot play the video, but you can imagine everything moves according to the train moves according to the tracks. I wouldn't call this emergent. It's more like it's not destroying the video priors, because everything in the training data, I imagine the trains, they always follow the tracks, right? And another thing is that it naturally generalized to multi-pokes. Although we only train on applying a single local force on the objects, you can directly trying to provide multiple Gaussian blobs, and it will just work. Okay.
Chen, can I ask a question again? Because the windmill is kind of intriguing. So you train on forces, but actually here's the torque. So do you convert that to a torque?
No, and you can also see that our representation is frustratingly naive, right? Because we kind of simplify our problem definition to test the hypothesis whether like we can inject the control signal at all using like a few amount of like non-photorealistic synthetic data. But I would imagine if you have a better representation that is calibrated with respect to the real world, other than this like the speed of the Gaussian blobs, maybe better things will happen. But again, then we need to come up with good training data to make sure we can train them properly. I'm not sure if that answers your question.
Yes, thank you.
Yeah, cool. And okay, and this is basically we trying to take like maybe 4 to 8 different like baseline papers. Every paper here we are showing relying on like some sort of physics simulator during generation time. And what we are showing here are not side-by-side comparisons. It's just that our fine-tuned neural network, fine-tuned only on synthetic data, can generalize and reproduce all of those scenarios in a reasonably realistic fashion. Okay. Again, I would take all the observations with optimism, but a lot of like detailed reservations, because like this is more like content creation, right? And they look nice, but do they really like work well if you care about the physics simulation? That we need much more rigorous study. And okay, so I will skip this, but we do need to have certain like certain engineering details to make sure our synthetic data is reasonably diverse to avoid shortcuts. Okay, so I will skip this. The takeaway, I have 3 more slides. Let me finish that. Takeaway, we show that a pure neural-based approach can lead to nice like force conditioned video generation. Okay, and the generalization behavior, it just works, right? How that happens, we have some hypotheses, but more things need to be investigated. And of course, our baseline video generative model is like 1.5 years old. So it would be great if we spend some engineering hours to improve to use a better model, which we indeed recall we show this example. The Coq Video X was what we showed, and the 2.2 is a better model. And now you probably understand why in our demos we never show object collision, because our base model never worked well on object collision. So we now switch to 2.2, okay, and then we also want to investigate a slightly different research question, that is trying to do, instead of force condition, we want to do goal conditioned, and which can be realized by a chain of actions. Okay, let me show just, I think this will be the snooker example will be the best one to show. Okay, so if you look at the bottom left corner, what I'm trying to specify is not a force applied to the yellow ball. What I'm trying to specify is that the yellow ball needs to be hit by another objects or a combination of objects to make the yellow ball to move to the bottom right. Okay, so you can imagine this is more like planning or like a slightly higher level like abstraction of like on top of the force or the chain of actions. And you can imagine that our model indeed works, okay? So, and it's also probabilistic. If you generate multiple samples, either it may use the red ball or the black ball to realize this goal, okay? And another interesting thing is that thanks to the video prior, it sort of utilized, I wouldn't say understand, but it utilized some of the physics constraints. For example, if my goal is to push this domino block to the left, then any of these three domino blocks to its right can be used to achieve the goal, but none of the domino blocks to the right of the gap should be used because there's a huge gap, right? And indeed, we draw many, many different samples, and it never occurred that any of the right are pushed. And similarly, if you put a ball in the box, then it shouldn't be used to try to push the other tennis ball. We have more examples, but I'm just showing it here for illustration. I'm out of time, but like we also try to use video generative models for robotic manipulation, and this is actually generated by our video generative model and then executed by a real robot, thanks to the other George, like George Konidaris' robotics lab. They kindly sponsor our real robot experiments. Basically, we're trying to translate a video generative model into like robotic policy by mapping the sequence of video frames into a sequence of robotic actions. I don't have time for detailed explanations, but you can imagine to make that happen, your video generative model need to be more accurate in terms of the quote-unquote physics simulation. That's it, and thank you everyone for listening, and happy to take a few more questions. Thank you.
Thank you so much for your great talk. Now we open the floor for questions. Jan Zhang is the first one who wants to ask a question.
Yeah, hi, Chen. It's quite interesting work. I have a question about the fine-tune part. So you are using the control net. I just searched for that. Basically, the idea is to copy a neural network exactly the same and take the control as input and to adjust the diffusion model, right? So it seems that it can achieve a general goal, right? Any kind of, now you are using the force. It seems
yes, exactly.
It's many possibility
yes
to fine tune or to enhance that.
Yes. So that's exactly right. And the challenge we were trying to address was the data issue. Like because in real world videos, it's hard to obtain the ground truth forces, right? And then our research question was more like, can we just use physics simulators to curate a reasonably small amount of training data, then use a control net to inject the control signal. And if you are interested in control net, please bear in mind that it may not work well for more recent generative models. And also it has a lot of black magic trying to make it work. So it's great, but it has a lot of like detailed engineering details that need to be figured out.
I see. And you also mentioned like the generalization of training, like fine tuning on relatively simple videos. So how can you guarantee, or you just try and it generalize?
We cannot guarantee, but again, like we tried several iterations of the fine tuning with control net, and then we have our human evaluations to make sure that some recipes actually work, but we don't really have a like principled explanation when it works. Okay.
Yeah, got it. Thank you so much.
Chen, by the way, Chen Zhang is also from Tsinghua University.
Yeah.
Yeah, nice to meet you.
Tsinghua is the best.
Thanks.
Okay, I can see Rodvik has a question.
Yeah, hi, Professor Chen. Glad to see your work again. So I had one question. So for example, like in the examples that we see here, right, where you're having like either you're having a blow of wind, something like that, or for example, you're poking an object. Essentially, when you're looking at it from the control signal sense, you're both of them tend to be like a same sense of control signal that you're inputting to the network. Like for example, let us say you try to expand it to some other task. Like for example, you take a cloth and you try to drench it in water. So those kind of activities where the control signals are kind of different. Do these methods extend to such kind of applications too?
That's a great question. So we haven't tried, so we don't know. But I think my personal opinion is that it really depends on like when the base video model will work without the force condition signal. And if it wouldn't work, we cannot make it work by training on synthetic data, if that makes sense. And
Right.
that's reflected in our like human evaluation as well. We cannot improve the motion or visual realism. Okay. And when those video generative models will work is also itself a very interesting question to explore. And you can tell that many of those videos nowadays are very good, nice looking, but still like in terms of the motion realism, it's probably not there yet, right? So open question, but at least for this work, we hypothesize that the progress will keep on going.
Okay. Yeah. Thank you.
Our second speaker is Dr. Suguru Shiratori. He will be giving a talk on Gimlet, generalizable and interpretable model learning through embedded thermodynamics. Dr. Suguru Shiratori is a professor at Tokyo City University, Japan, and a visiting scholar in the Crunch group right now. He received his PhD from the Tokyo Metropolitan Institute of Technology in 2007. After 10 years as a researcher at Canon Inc., he joined Tokyo City University in 2017 and became a full professor in 2024. He has served as an editor of the International Journal of Microgravity Science and Applications since 2017. His research focuses on modeling and numerical methods for thin film and surface tension driven flows, thermofluidics in microgravity, and more recently, physics-informed machine learning for thin film flows. With that short introduction, the floor is yours and you can start your presentation.
Thank you. Thank you for introduction. Hi, everyone. I'm Suguru. So today I will talk about the data-driven discovery of the physics model. This is a collaborative work with Elham, Raj, and George in my visiting at Brown University. So, okay, many of you are familiar with the numerical simulation of some physical model, physical phenomena, and usually we select the governing equation, then we implement the governing equation on the code and execute. Then we check the result with the real observation. And sometimes this result have a much discrepancy from the observation. So for that case, we have to go back to the selection of the physics or some tuning of the parameter or to find the missing physics or something like that. So this kind of things take much effort for us. The motivation of this work is to discover the unknown or misspecified physics from the data. In conventional approach, we either have to take a trial and errors to discover the physics, or just rely on the expert like Johannes Kepler. And in modern approach, the research field of the data-driven discovery of physics has been an emerging paradigm. Then in previous research, a number of methods for the discovering physics has been proposed. Here is, I summarized the method. This method can be roughly categorized into three types. The neural operators such as Fourier neural operator or deep on it. This kind of operator map the function, the mapping from the function spaces. And these neural operator can be physics informed, but now we are considering the discovery of the physics. So the physics informed approach cannot be, this is not available for this program. Then the second one is the genetic programming. This construct the mathematical expression by evolving the combination of the candidate function. The last one is the sparse identification. This method finds the sparse linear combination of the candidate functions. The latter two approaches can be grouped together as a symbolic regressions. So here I summarize the pros and cons of the previous methods in terms of the generalizability, interpretability, and library-free capabilities. The neural operator is basically not interpretable and the library-free capability it has. For the good generalizability, we need a lot of data for training. Then on the other hand, the symbolic regression is basically interpretable because they try to find explicit mathematical expression, and but we need very good prescribed candidate function library. So this is the one of the bottleneck to apply the real phenomena, real problem. And if the good appropriate function is missing in the library, this method is never generalizable. So the previously reported proposed method are some part of this capability is missing. We propose a new methodology we call Generative that is generalizable, interpretable, and library-free. So Generative has all these capabilities. So how to realize this method is the problem. Then for the generalizability, we rely on the variational principle and the functional form. And then for the interpretability, we rely on the thermodynamics. Thermodynamics is among the most universal and transferable description of the physics system, in my opinion. And for library-free capability, we don't use the explicit symbolic formulation. We just represent the model by neural networks. So the model is the somehow gray box learning. So I'm not sure how many of you are familiar with the variational principles. So I will explain a little bit about it. So this might be somehow boring for the familiar persons. So by solving the governing equation, of course, we can get the solution of the equation. When we solve the variational principle, we can obtain the governing equation. So here, the delta I over delta U is the variational derivative. As you know, of course, the function is the mapping from the value to value, the value to value mapping. Then the derivative of the function means that how much the mapped value change if we change the input value. Then on the other hand, the functional is a function of the function. For example, we define the functional as the integral of some local function f. Then this is the mapping from function to the value I. Then the functional derivative is defined as shown here. So this means how much the mapped value changes if we change the input function. So this is the functional derivative. This functional derivative is really essential to describe the variational principle. In the standard variational principle, we define the Lagrangian as the difference between the kinetic energy and the potential energy here. Here, phi is the, let's say, the solution field depending on the position and the time. Then we consider the action path as a volume and the time integral of the Lagrangian. If we have some constraint that can be written in a form of the u phi equals 0, we can consider this constraint into the action path by the Lagrange multiplier method, like here. By solving this action path, least action path, that means that stationary condition of the action path, we need a variational function derivative. That means that function derivative becomes 0. So if we can solve this problem, we can obtain the governing equation of the problem. So the realizable motion corresponds to the stationary condition of the action path. So this way we can get the governing equation. And why we can get the governing equation from the least action path action path principle is interesting and really fundamental. Here we consider the simplified ODE, ordinary governing equation, the differential equation, depending on the time. So suppose the xt is the displacement and x dot t is the velocity. Then we define the Lagrangian as a two-variable function, like here. Then we consider the time derivative of Lagrangian, dl dt. This can be decomposed into this term by the chain rule, and further converted to this equation. Then we obtain the identity equation shown in the bottom line. So this means if the green one becomes zero, the brown time derivative of the brown one is satisfied. This can be we can regard this is the conservative form. Actually, the green one is correspond to the momentum equation. In other word, Euler-Lagrange equation, and the green one correspond to the energy, total energy of the system. Then the dE dt is the energy conservation form. So this is the very basic of the Lagrangian mechanics. So here we let us consider the very simple example of the mass spring problem. We consider the motion of the mass connected with the spring. Let's say that m is the mass of the object. The small k is the spring constant of the spring. The kinetic energy and the potential energy can be written here. Then the total energy is the summation of the both energies. Then we consider the Lagrangian. We define the Lagrangian as the difference between kinetic energy and the potential energy here, and we define the action path as a time integral of Lagrangian here. Then we consider the stationary condition of the action path by the functional derivative. So we consider a little bit different function. So the effect of the difference of the function. So okay, so we can convert to this equation, and okay, so this term can be rewritten in as this form, this equation. And the second term in the integral can be decomposed into the two terms here. And the gray one can be eliminated because this is the time derivative, so it is easily integrated. And in the t equals 0 and t equals t0 and t equals t1, the variation delta x should be zero. So we can just eliminate the third term. So we can obtain the last line. So then delta x is the arbitrary variation. So for the identity equation, the green one must be 0. So this is corresponding to the momentum equation. And so let's remind that this identity equation, if the green one is satisfied, automatically the energy conservation is satisfied. This is the very simple explanation of the Lagrangian mechanics and variation principle. Then next we consider the thermodynamics version. And in the equilibrium thermodynamics, the variation principle can be expressed by the stationary condition of the Helmholtz free energy. Here, the capital F is the system's total Helmholtz free energy. Then this functional derivative of the total free energy is 0. This is the equilibrium thermodynamic, the variation principle. But for the fluid flow problem, we have to consider the non-equilibrium process. But the non-equilibrium thermodynamics is still developing and not completely established. The old conventional, the really early work by Ginsburg and Landau, they just suggested the time evolution version of the variation principle right here. This equation means that the time evolution of the system can be written as the system is going to the direction where the system total energy decreases. So this is just a suggestion, not derived equation. Then after that, Onsaga derived the variation principle which is available for the dissipative processes, right here. So this is very sophisticated and really powerful tool to describe the complex phenomena such as soft motors or very complicated fluid. But from Onsaga's variation principle, we cannot derive the convective term. So this cannot be directly applied to the fluid flow physics, fluid flow phenomena. Then recently, Fukagawa and Fujitani derived another version, another formulation of the variation of principle based on the reaction path of the fluid particle. And this is specific for the fluid flows. And by this variation principle, we can obtain the convective term, so the full form of the Navier-Stokes equation. So we take this version of the variation principle in our work. Then in this study, we want to discover the physics by the data-driven approach. Then we focus on the fluid flow and the scalar transport problem. So here we define U as the velocity, P is the pressure, phi is the mass fraction of the one component. We consider binary mixture, and the phi is the one of mass fraction of one component. The rho is density here. Then we assume that we know already the convective term appear in the governing equation. our goal is to discover the constitutive models and the diffusive fluxes. For example, the stress-strain relation or diffusive flux. This is the target terms to be discovered. Then we consider the variational principle for this problem. In a variational principle of the Fukagawa and Fujitani's version, internal energy is considered to be dependent of the density and entropy S here. We considered additional free energy due to the mass fraction phi here. And we take its contribution to the internal energy here. So this is the modification of the variational principle of Fukagawa and Fujitani. And time evolution, the entropy can be written as here. So here, theta is the dissipation function that describe how the entropy increases. Then we regard these two functions, functional g and theta, as the unknown term, and we try to discover from the data, observation data. Then small g and small theta is the local function, and capital G and capital theta is the volume integral. And that means the system's total energy and the dissipation. Then we consider the variational principle by defining the Lagrangian as the difference between kinetic energy and internal energy. Then we define action path as the volume integral of the Lagrangian and some constraint. Here we have 4 constraints. This is the mass conservation. And I think I have already introduced many parts of this formulation so far, but capital A here, I didn't explain. This capital A is actually related to the description of the fluid motion. There are two, there are two descriptions for the fluid motion: Lagrangian description and the Eulerian description. In Lagrangian description, we label a fluid particle with its initial position, small a here, and we write the current position by large X here on the current time t. Then velocity u can be defined as the time derivative of capital X here. On the other hand, in Eulerian description, the coordinate is expressed as a spatially fixed frame, fixed position of X, small x here. Then to label the fluid particle, we need the mapping from the Eulerian coordinate to the Lagrangian coordinates. This mapping is expressed by capital A here. Then because this mapping A is the Lagrangian coordinate, so this Lagrangian coordinate conserved along the fluid motion, fluid path. So this conservation equation must be considered as the constraint. And also we have to fix the end of the path line. So the variation of A, capital A, should be 0. So this is the additional constraint. Here we are back to the variation principle. We have 4 constraints here. Then first 3 constraints are holonomic constraint. And that means these can be imposed by Lagrange multiplier in the action path integral here. But the last one, the time evolution of the entropy, this is the non-holonomic constraint. So we cannot impose by the Lagrange multiplier. So we have to consider separately. The holonomic constraint is the constraint that can be written in a time-independent form, like here. For the case, if the constraint is given in the form, including the time derivative here, we think about the integration of this original form by like this here. Integrate this if the system is integrable. The gray term, the second term in the integral here, the second term here vanishes because the variation of x here at the time t equals 0 and t equals t1 vanishes. So the first term can be used as a Lagrange multiplier method. So this can be integrated in the action path integral. On the other hand, the non-holonomic constraint cannot be written in an integrated form. So that means the Lagrange multiplier method is not available. So we have to separately apply this constraint into the least action path. The detail of how we apply this non-holonomic constraint is written in the original paper of Kagawa and Fujitani. So finally, we can solve the variational principle of our problem. So here is the internal energy with additional Gibbs energy, free energy here. And we define the Lagrangian as the difference between kinetic energy and the internal energy here. The action path is the time and the volume integral. And here the holonomic constraints are included in the action path with the Lagrange multiplier. And we have to consider non-holonomic constraints of the entropy evolution separately. Then we take the variation of the action path with respect to the all unknowns. So rho, u, and entropy s, mass fraction phi, in k, Lagrange multiplier k, beta, and a. So this is the really many couple of equations. So but basically we can solve this problem. So here is the resulting equation. This is the basic form of the governing equation used for the discovery. So g and theta is the unknown term that can be regarded as the unknown physical model. Then here, free energy functional g is the volume integral of local function g, and this special function also can be written in this form. Then this functional g and theta can be written in the series expansion of written here. So the derivative of the local function as with respect to the original function solution here. And also g is depending on the spatial derivative of the solution field. And we can written in the series expansion of spatial derivatives. So based on this concept, we construct the overall machine learning framework. So here is the schematic of the total framework of our methodology. We have 3 neural networks. One of them is the pin, the very standard playing pin here. And another neural network is free energy net, and last one is dissipation net here. So I explain from the total loss function here. The total loss function is defined as the summation of data loss and physics loss and some regularization loss. For data loss, this is very simple. So let's say we have the measurement data here, and we evaluate the data loss as the mean mean square error between the predicted solution and the measurement. And for the evaluation of physics laws, this is a little bit complicated. So after we predicted the solution field here, we take the auto differentiation, and for known terms, we can just substitute these terms into the governing equation. For the unknown terms, we need more process. So after we take a auto differentiation, we put this solution field or the spatial derivative into the free energy net or dissipation net here. These two neural networks predict the free energy function and dissipation function. Then after that, we take the automatic differentiation of these two energy functions with respect to the solution field here. Then we can obtain the functional derivative of these energy functions. These functional derivative can be substituted in the governing equation here. Then we can evaluate the error of the governing equation. So this is the physics loss. Then the simultaneously minimizing the total loss function, we can obtain the free energy function that just best fit the observation data. This is the basic approach. We call this method as GIMRET as an acronym of these words. Then I have to explain the detail of the these two neural networks. The free energy net is composed by the integral neural networks proposed by the previous research here. In our method, we just need the derivative of the free energy G here. So in the training, we just only need the derivative, but to see how the energy function is, we need an integrated function G here. So that's why we use the integral neural network. The integral neural network is designed to obtain the derivative form and the integrated form simultaneously. In the standard neural network, here is the description of the standard neural network. So we have hidden unit here and activated unit. Here sigma is the activation function. Then the output layer is written here. Then this mathematical expression can be easily differentiated. So we can obtain the derivative form of the standard neural network here. So we have the additional activated unit here. The output layer can be written as here. So using the same weight function, the bias, and activated function, we can obtain the original function and the derivative form at the same time. Then we use only the derivative form to the training. After the training, we can see the integrated function here. So this is the integral neural network. And then next, we have to explain the dissipation net. Dissipation net is used to predict the dissipation function here. The dissipation function must be a convex function. So we apply the convexity, we impose the convexity to the neural networks. This is the from previously reported paper. So the input convex neural network is designed so that the convexity with respect to the C here is guaranteed. So the non-negative sum of convex function are also convex, and the composition of the convex and convex non-decreasing function is also convex. So using this property, we can design the convex neural network here. Okay, then I finished the explanation here. So the next one is how to calculate the functional derivative here. So this functional derivative can be, all these functional derivative can be calculated by the automatic differentiation. Let's say we have the pin here, and we have the energy net here. Then this pin predict the solution phi here. So to obtain the spatial derivative phi, this is very simple, the standard way of the this automatic differentiation. Then we take this phi and the nabla phi, a grad phi, to the input of energy net. Then this energy net predicts the free energy function G. Then after that, we take an automatic differentiation of the G with respect to phi here, or G with respect to the grad phi here. Then we can obtain this functional derivative, and also we need a spatial derivative of this function, so we can calculate this root by the automatic differentiation using this root. So it takes a little bit long calculation, but basically we can calculate all these terms by automatic differentiation. The key point of this work is that we realize that this calculation of the functional derivatives. So this is the code snippet for TensorFlow. So we just take a gradient tape, additional gradient tape here. Then after we got the phi, we take a derivative of the phi, and we take this px to the energy net. Then we can calculate the derivative of this g phi x like this one. This is very simple code. Okay, so the final task is to optimize the loss function. The total optimization problem can be written here. So we have 3 neural networks parameterized by lambda and gamma g and gamma theta. These are the weight and the bias values for the 3 neural networks. This can be minimized by minimizing the total loss function. The total loss function is defined as the summation of the physics loss and data loss and some regularization loss. For the regularization loss, we consider the L2 normalization, regularization, and some other normalization. I will explain this one later. Then please note that the solution field include the pressure here, but the measured data, we don't use the pressure because in the fluid flow problem, it is extremely difficult to obtain the flow field and pressure in the same time, same position. So we don't use the pressure data, just use the velocity data. Then regularization loss, for the regularization loss, we take the L2 regularization, and JG and J theta here is designed for the scaling of the free energy net to let the output of this neural network as order 1. So these are designed for some well-posedness of the problem. The final one is the pressure references for some fluid flow problem. The beta L2 or beta G, beta theta, beta H is just the weight of these regularization loss. some part of these regulations are not used depending on the problem. Okay, and for the optimizer, we use the first the Adam optimizer for the first 1,000 epochs, and then we switched the optimizer to the SS Broyden, self-scaled version of the Broyden. This is recently known as the one of the best optimizer for the pin-related machine learning. And also we use the resampling of the residual point by LAD, residual-based adaptive distribution. Okay, so we see how this method works for the validation. For the validation problem, we consider these four problems. Due to the time constraint, I explained two flow problems. One of them is the Newtonian fluid Navier-Stokes equation. Another one is a non-Newtonian problem. So this is the problem set up for validation. We consider the steady state flow by Navier-Stokes equation for Newtonian fluid. Then this is the full original equation. Then we consider the viscous term is unknown. So this is target to be discovered. The equivalent form for this equation can be written here using the dissipation function here. The true form of the dissipation function is here. And the large theta here is the volume integration of local function here. So we will see if our method can recover this local dissipation function. For the data set, we prepared the two different flow data. One of them is data A is the lead-driven cavity flow program of the Reynolds 400. Then another one is quite different program, the flow past cylinder with Reynolds number 20. Then first we apply this model discovery and we check if the dissipation function is properly discovered here. After that, we fix this discovered function theta, then we transfer this model to the other completely different program. Then we check if the model can be applied, can be available for the proper cylinder. So this is the definition of the loss function, similar to that I explained before. The different part is just here. So we need a pressure reference because we don't use the pressure data for the training. So we need a pressure reference. So we set the XP and YP at some specific point, and we take this pressure becomes some specific value, actually 0. This is the history of loss function. The first 1,000 steps is Adam, and after process is optimized by SS Broyden. Then total loss function decreased below the 10 to the power minus 7 here, order of the 10 to the minus 8 here, the really good convergence. Here is the raw field predicted by the Gimlet, our method, and middle one is the original data, CFD data calculated by OpenFOAM. The right side is the difference between them. The maximum error was 0.5%, so really good accuracy. Then we check this discovered function theta can be applied for the other program, proper cylinder. Here's the result. Left one is the Gimlet, and the middle is the data calculated by Nectar, and the right is the difference between them. The maximum error is 0.01, so this is also a good result. Okay, so we confirmed that our method is really generalizable. In this training, we applied the model learned from the Reynolds 400, and we applied to the different Reynolds number. So we have to consider how we treat the difference between the Reynolds number between the program. So to do this, we introduced another training parameter here, alpha here, to express the difference of the Reynolds number. Then this is the result of the training of the ratio of Reynolds number here. So the truth should be 20 because the ratio of Reynolds number is 20. So the first initial value we set 1 here, and during the training, this alpha exceed to the really close to the truth value, just a 0.56% error. So this is really accurate. Then next I explain the generalizability of the how to improve the generalizability. Here is the discover dissipation function. Actually, the dissipation function here is the function of the 4 variable. Then it's difficult to show the shape of the function. So I plotted the projected shape to the one of these input variable. So the left one is the function theta as a function of del u del x, so that we see the 4 different shaped function. Then the left side is how the dissipation function is trained for the data. So this is only plotted for the data. So the correlation factor is really close to 1. So at least for the trained data range, the accuracy is very good. But for the projected space, there are not correct area, or even for the data range. So I want to consider how to improve the generalizability. And to do this, I considered that data augmentation. So that means we use more data to train the model. So we prepared many pins to describe the solution of the different data, and we prepared the common one dissipation net here. So for different pin, we use just a common single dissipation net to describe the unknown physics. By do this, we can improve the generalizability of the round function. The upper part is the original data result, which I showed previously. The lower part is the result for the data augmented. Actually, 5 rotated data we used. Then this dashed line is the truth. The green solid line is trained data, a trained function. So we can clearly see the generalizability is really improved. Okay, so last thing is the non-Newtonian fluid problem. So similarly, we consider the problem of the 2D steady state problem. Then for the stress strain constitutive model, we selected the Bard cross Karyu Yasuda model, like written as here, the really complicated relation of the viscosity. Then we tried to discover this complicated and constitutive model. Then we prepared 2 data sets for the data-driven cavity problem. One of them is Reynolds 400, another one is Reynolds 100. Then first we discovered the special function from the data A. Then we fix theta, and we transfer the model to the data set B. Then we check if the model can be applied for this data. So this here you see the result. Upper part is the discovery part. So the left one is the predicted by Generative. Middle one is open form. The difference between them is right-hand side. The lower part is application part. So this is also good accuracy. And this is here you see the round this special function. Then I also applied the handling of the difference in the Reynolds number here. The alpha is also the training parameter for in the training, and the ratio of the Reynolds number exceed really close to the true value here. So also for the non-Newtonian complex fluid problem, this method is really showed really good accuracy. So let me wrap up my talk. We achieved the Generative. We proposed a Generative that is generalizable and interpretable and library-free. In the future work, remaining challenges, the validation we tested so far is just a synthetic data. So we needed to apply for the real observation data. And this method, I think this method can be extended to another further complicated problem. For example, viscoacidic fluid models or the phase change phenomena and turbulence model discovery. That's all. And the preprint is available on the archive, and the paper is now under review. After the publication, we are going to upload the code and all data on the GitHub. Thank you. So I'm happy to have any question you might have.
Thank you, Suguru, for the great talk. So now we open the floor for questions. Do we have any questions for the speaker?
Hi, Suguru. This was a really nice talk. Thank you for sharing.
Thank you.
Maybe one quick question, like when you maybe to learn in some sense to learn the missing term of the PD, you need some type of data, right? Did you try to see what happens with the data, or maybe you explained it but I missed it? Do you try to see what happens when you add noise to the data? How sensitive is the model to recognize the missing term with noise?
Okay, so actually, we just checked the effect of noise here. This is for the Burgers equation problem. So left hand is the clean data result. So the noise is 0%. So the upper part is the loss function. The loss function decreases at really good, really lower level. And the lower part is the discovered function. The blue line is discovered function, and the dashed red line is truth. So even for the outer data range, the discovered really good accuracy. But for the noisy data, so we just put the 5% of the Gaussian noise, then the data loss doesn't go lower. So R is stopped at the level of order of 10 to the -3 here. But the discovered function is not bad. At least for the data range, the accuracy is really good. But the generalizability is a little bit lower than the clean data case. It makes sense?
Okay. Yeah, that makes a lot of sense. And also because since you're using second order optimizers, and even with this resampling thing that you're using, they tend to be a bit sensitive towards noise. And also another question, I saw that when you transfer your learn function, for example, from Reynolds 400 to Reynolds 20 in the case of the incompressible, or to Reynolds 100 in the case of the when with the non-Newtonian fluid. Did you try to see what happens if you go a little bit farther away? Like, for example, what if you started with 100 and to see what happens if you try to go to, I don't know, 1000, when, because arguably the dynamics does not change that much in that Reynolds range, right?
You mean, for example, if what happen if we run for the Reynolds 100 and apply for the higher Reynolds number? So
yeah, let's say 1000.
Extrapolation. How the exploration is possible is depending on the data range discovered. Then, so basically, the validation we tried is run from the wide range and applied to the narrow range from the original data. So if we take this kind of thing, so data augmentation, we can make wider range wider for the applicable range. So by doing this kind of thing, we can apply for the even for extrapolating range of the Reynolds number.
Okay, that's really cool. And maybe the last question, if nobody else has another question, did you try it with experimental data? Like, because then it would be really cool to see what happens, because there are sometimes that you think that this was the right equation, but actually it's not. So it would be really nice to see what if you get something interesting there.
Yeah, that to apply the experimental data is the next challenge for us.
Okay, but that was a really good talk. Thank you so much for sharing.
Thank you.
Thank you. Do we have any other questions for the speaker? Yeah, Sanju.
Thanks for your presentation, Professor Shiratori.
Thank you.
So I have one question and the following small question. So the one is that, can this work based on the Lagrangian formulation be expanded to Hamiltonian formulation with no requirement of zero variation at the end points? And do you think that approach is worth to try? So I wanted to ask you this question.
This time we applied the Lagrangian approach, but basically the Hamiltonian approach is in principle possible. But the problem is how to know the generalize the position and generalize the momentum. This is the actual problem to apply the realistic problem. Does it make sense? That answer to your question?
Yes. Thank you.
Sanjun, can you introduce yourself? Who are you?
So my name is Sangjun Park, and I officially received the offer from Brown University, and Professor George Karnitakis kindly invited me to this crunch seminar. So even though I'm not officially entered to Brown University PhD program, but I'm here thanks to his support.
Nice to meet you.
Thank you. Nice to meet you.
Anyways, welcome to Crunch Group.
Thank you.
Do we have any other questions, any comments for the presentation? I think no. Thank you so much, Suguru, for the presentation. And thank you, everybody, for joining us today. It's time to close the session. Have a great weekend. Bye.